It's great to be here. So today I want to talk about progressive web apps and more importantly, the impact and the value that it brings to the end user experience. I'm going to start with a little background. As Brent mentioned, I work for a company called Flipkart, which is one of the largest e-commerce players in India. Now, one of the key focus of Flipkart has been on mobile. So recently we launched a mobile website known as Flipkart Lite. Flipkart Lite is a progressive web app, and I was lucky to be a part of that incredible team that built it. However, early last year, we actually shut down our mobile website. So Flipkart decided to become an app-only platform, and there were certain core insights which went behind taking this decision. So one of them was that we really want to give a compelling user experience on mobile. And at that point, we realized we just couldn't do it with the mobile web. So what is that makes native apps better than the web? That's the question we asked once we shut down our mobile website. And in retrospect, we basically identified some 3 core pillars that gives the native apps edge over the mobile web apps. That's high performance, the immersiveness, and the engaging tools that native apps have. We decided that we're going to bring all this goodness to the mobile web, and that was the genesis of Flipkart Lite. So let's look at how to do this. We start with high performance. There's a consistent feedback that native apps always feel somehow instant when they load. You can open an icon and it just quickly loads. There is no white screen. I call it the white screen of death. You don't see that much. The interactions are smooth and it's all fluid. So can we do this on mobile web? Let's solve for instant load first. The Rail model from Chrome says that to give a good user experience, you should load your web app within 1000 ms or within 1 second. Now that's almost impossible to do on mobile networks where the connections can be really flaky. These are some of the numbers from the different ways of web apps that we have built previously at Flipkart and how they fare on a 2G, 3G network. Now it's important to remember that in a country like India, more than 80% of our users on a 2G connection. We saw that even the traditional server-side rendered apps, they have quite a lot of time before the user sees anything on his screen. And so with the client-side apps, you save a little bit on the network side with client-side apps because there's less server-side processing, but then you add on to the main thread rendering time, because parsing JavaScript and CSS is quite slow on low-end devices. And these low-end devices are like everywhere in India. So the obvious next step to go from there was to go isomorphic or universal, right? I mean, we bring the goodness of the server-side rendering, and we also add the goodness of client-side apps where the navigations are really instant. However, we identified a couple of problems with isomorphic or the traditional way of doing server-side rendering. And I'm going to talk about those in a while, but before I go to the next slide, I need you all to keep an open mind. And I promise you I'll come back to the problems of isomorphic or universal. So this is the approach that we went with. It's known as the App Shell architecture. In simple words, App Shells are nothing but HTML pages that represent the basic structure or the outline of what your final app will look like. The way you do this is by breaking down your entire application into 2 states, a loading state and a loaded state. Here's an example from the search results page on Flipkart Lite. As you can see, the loading state has placeholders or loaders for the final content to come in. And this is what the app shell is. The app shell is like a host for the dynamic content to come fill in. The loading state or the app shell makes for a very good first paint for the user. Now, in a complex JavaScript client-side app, you can't just divide your entire application into loading state and loaded state. It might be really hard to do that. Luckily, we use React, and thanks to React's declarative model, we could actually have declarative app shells. This is a gist of what it looks like. We just have a state called loading, and based on that, we flip components to either loaders or the components that have the content. This is obviously the very simplified version of what it is in real life, but this basically highlights how to go about this. With the initial state as loading true, we can actually render this on server side, and you can generate app shells, right? Now, there's a problem. In our deployment with a large-scale React app, we saw that render to string can actually be quite CPU intensive. That means, and it also can't really stream HTML as of today. So that basically means that render to string is a sort of a blocking call, adding latencies to the first print for your end user. Now, the good thing about app shells are that they're completely static, right? They don't have any dynamic elements to it. So that means we could generate all of these app shells during build time. So we shifted all the heavy lifting to build time, and on the runtime, when a request comes in, we just serve the HTMLs as is. There's no processing. So we have eliminated all server-side processing time. Now, this can be really hard to do, right? Mind you, like getting rid of all the dynamic elements from your HTML, including session info and anything else that you might embed is really hard to do. But when you do it, once you achieve it, the benefits are immense. The way we render this on the server is we have a bunch of React routes defined. And during a build step, we inject them with some dummy parameters and generate the corresponding shells. The important thing to note here is that we have a single shell for all the URLs of the same type. You know, at Flipkart, we have a catalog of over 30 million products. That means we have 30 million unique product page URLs. But thanks to the app shell architecture, we can have the same shell across these 30 million URLs. So let's see how that fared in our 2G connections. We obviously saw a lot of improvement on our network time because we eliminated the server processing time, as well as we did some optimizations like inlining the critical CSS to render the app shell and making the rest of the CSS asynchronous, including the JS, which was asynchronous as well. And thus, we also reduced the time on the rendering main thread, which still brought us around 4 seconds. On repeat visits, this was still around 1.2 seconds, even with app shell. Now, when you think about it, 1.2 seconds of the white page of death is a poor experience, especially compared to native apps. You don't see a lot of white page on native apps. Now, we didn't want to do that. We wanted to give a really compelling user experience. So the pattern that emerged from solving this was going offline first. The essence of offline first is basically you treat network as a progressive enhancement, which means that you try to respond to all your critical resources from cache instead of going to network, and only go to the network for very essential or critical data. This is basically the model of apps, right? When you install a native app, you're actually prefetching all the required critical resources for it to show the first render. We want to bring the same model to the web. And the way to do this is service workers, of course. How many of you have heard or know about service workers, have used it? All right, that's a fair bunch. Well, for those who haven't, it's a new standard. Service worker is essentially a type of a shared web worker, but the way it behaves is it acts like a network proxy, where once it's installed, it intercepts all the network requests that go from your web page. And at the service worker, you have a programmable cache, which you can use to decide if you want to serve the request from the cache or go to the network. So it's highly programmable. It's a very low-level primitive API. And it's event-driven. So service worker lives beyond the scope of the browser. Even with the browser closed, the service worker is still there. It might be in a dormant state, but it's still there. One prerequisite for service worker is TLS. So your page has to be on HTTPS to have service worker. Like I said, with service workers, you can program very robust strategies to handle your network requests. And some of these are, cache first is when you would try to look for the response in the cache, and if not, then go to the network. This works for your static resources, which are usually versioned, so you can blindly just return from cache first. Another strategy is network first, where for some critical data, you'll try to hit the network first, but in case the network fails, or if the user is offline, or it times out, you can actually fall back to the cache and respond from there. Fastest is my favorite strategy, which is essentially a race between the cache and network. Now, this might seem kind of weird to do, like why would you even race between a cache on local and network? But mind you, on some low-end devices, disk I/O can be actually slower than responding from a Wi-Fi network. But this fastest strategy is also in some way an implementation of read-through cache, which means that what we do is return the response from the cache, but in the background from the service worker, we still make a network request to get the updated or the next version of that cache. This is very useful for our app shells because we respond back to the app shells from the cache, but then in the background, we make the request for the next app shell if the app shell is updated. So, writing service worker code can get quite tedious, and it easily gets hard to maintain. So we use a library called SW Toolbox. It's a sort of a wrapper library over service worker. Think of it as the React for service worker. It lets you write declarative routes and map different strategies to it. So here's an example of what SW Toolbox code looks like. You can easily define routes and have strategies corresponding to those routes. You can also give some options like cache name. SW Toolbox also adds some new capabilities like max entries, which allows you to have an LRU-based cache so that you don't bloat your cache with too many resources. There's also things like max 8 seconds, where you can define a TTL for your cache to purge automatically. Great. So the impact of this was, on 2G connections, we brought down the response for all of our critical resources within a few ms. This means we've basically eliminated all network latencies in our critical path. So our time to first paint is now within 300 ms, thanks to service worker. Beat that native apps. And also the other advantage here is that it also works offline. Because of service workers, we can always fall back to the cache when network is not available. So as I promised, I'm going to compare the app shell architecture to the conventional server-side rendering. Let's look at the first parameter, which is, does it help improve the first paint? Yes, the conventional server-side rendering is known to help you improve the first paint, and it's a recommended approach for that, and so does app shell. Build time rendering is something that you cannot do with the conventional server-side rendering, because that HTML contains dynamic data which you have to generate per request. But with app shells, you can just offload all that work during build time. Client-side cache, well, again, doesn't work with the traditional HTML rendered pages, but it definitely works with app shell. And again, as I mentioned, the app shells can be reused across millions of URLs of the same type. SEO is a little tricky with app shells. We know that it works perfectly well with server-rendered pages, but with app shell, it's something that you have to try it out yourself. If you've been able to solve SEO for a single-page app before, you should be able to do it for app shells as well. The key theme here is that it's all about perceived performance. All of these numbers that I showed you wouldn't matter if users didn't perceive this as a really instant load or a really speedy thing. So one of the patterns that we do to sort of amplify the perceived performance is reuse store data. Now, we use a in-house store Flux implementation, and with that we have stores. And the way we have modeled our store is that they can be reused across different pages and components. So here's a demo of what that looks like. What you're seeing here is a search result page on Flipkart Lite. Once the results are loaded, we have populated the stores with the product info. And what I'm going to do in a second is going to navigate to one of those product pages, and we'll try to reuse the data from that store. So if you see, you didn't see a single second of a white page. We reused the image, product info, and some essential bits from the browser results and brought them back to the product page. And after that, things like the buy button and the offer and the carousel loaded progressively. Again, a key piece of performance is how smooth and fluid your animations are. Now, we have done a lot of work on optimizing each and every animation on Flipkart Lite. But in general, if you just follow some basic best practices, you can do really well here. Some of the things like just using opacity and transforms for all your interactions and transitions, using should component update in your React components, try to avoid sync storage like local storage, move to an async storage. And there's tons of room to do more. You're going to hear an entire talk on this tomorrow. There's one quick win that I want to call out, which is most modern browsers today support rasterization on the GPU on most mobile devices. And all you have to do to enable this is, at least on Chrome, is add this meta tag with content width, device width, and minimum scale 1.0. Just adding this one line of code, and you will see immense difference in your rendering performance. So I urge all of you to go ahead and do this. The bottom line is that there is always room for optimization. It's relatively easy to build fast apps, but it's really hard to keep them fast. So performance optimization is supposed to be a continuous process, and you'll have to incrementally keep adding more and more optimizations. It's a never-ending thing. All right, So the next pillar that we identified on making a great experience was the immersiveness. Native apps are these first-class citizens that live on your app home screen, are on the app menu, and you can just open them with one tap in this fully immersive, full-screen experience. Unfortunately, on the web, we have always been stuck in a browser tab. The good thing is that that's changing with this add to home screen function. This is a way for us to actually escape the browser tab. Add to home screen prompts the user to add the web app to the home screen, which basically makes your web app installable in some sense. Of course, there are some certain requirements that you have to meet. Number one is have a service worker, because obviously when a user taps the home screen icon, you don't want to end up showing a dinosaur. It should be on TLS, which is also a requirement for service worker. You should have a valid manifest. We'll talk about that just in a second. And there's a certain heuristic that different browsers will have that you need to meet. This heuristic is in place to make sure that the user is engaged with your web app enough before the prompt shows up. Otherwise, every website you visit would just show up the prompt, and that does no one good. This is what the manifest looks like. You can link the manifest from your HTML at the URL /manifest.json. And the manifest has this bunch of attributes that represent all the meta information about your web applications. The attributes like name, short name, icon, and start URL is what would be required for the add to home screen prompt to show up. The start URL is pretty interesting because it's what differentiates this home screen icon from a traditional bookmark. Your bookmark is basically a shortcut to a specific link in your web app, whereas the home screen icon is actually an entry point to your app wherever it starts, right? The background color and the icon will actually generate a splash screen for you, and the theme color will theme the top-level status bar in your Android phone. So I have a demo of what this immersive experience looks like. I'm going to start by tapping on the home screen icon, and it's going to open with a splash screen. You see it's a full screen experience. Gone is the URL bar. You look at the interactions. They're smooth and really fluid. The UI stays responsive all the time. We give touch feedback to the user. The data loads quickly. You don't see a white screen anywhere. And in general, the app feels truly responsive. Now I'm going to go to the airplane mode, and here's what it looks like offline. Instead of showing the dinosaur, you can still revisit the last product page that you had visited. And this works even if you refresh the page. So this is the current experience on Flipkart Lite. All right, so we've cracked high performance, we've cracked immersive. The last piece of the puzzle is re-engagement. Native has this incredible engagement tool, which is push notifications, which has lacked from the web for a long time. Fortunately, thanks to service workers, we can even send push notifications now. As I said, service worker is a web worker that lives beyond the scope of the browser. So the service worker is always there in a dormant state. And once it's registered to a push service like GCM, your server can send a push to the GCM, which will wake up the service worker and give a push event inside your service worker. On that event, you can fetch the data that you want to show for the notification and use the notification API to actually display a notification. So this is possible as of today on Chrome and Firefox, right? And Facebook has been doing this for a while now in production, and it's worked incredibly well for them. It's launching soon on Flipkart Lite as well. There's an extensive guide on how to enable push notifications for your web app today. I recommend you all check it out at bit.ly/webpushguide. All right, so all of these items put together, all of these functions and great technologies put together embodies what is known as a progressive web app. So what is the progressive in this progressive web app? The idea is that a progressive web app is nothing but a normal web app that opens in your browser. When you click a link, it opens up in your browser. But the more you engage with it, the more you interact with it, it gets powerful, it gets immersive, and it behaves like a native app. When we launched Flipkart Lite, we saw some incredible feedback on the goodness of Flipkart Lite, and there was a common theme around how it worked flawlessly even on 2G networks. So this sort of highlights the importance of perceived performance. Another feedback was how incredibly smooth it was, and that just by following some basic best practices we could achieve. I really like the first tweet here. It says if you haven't checked out Flipkart.com and Chrome Android phone yet, you're missing out on the future of the web. And that's the note I want to end with, that the future of the web is already here. Technologies like React, service workers, are transformative in nature and allow us to build really compelling, stellar, and delightful user experiences. And it's up to developers like us to go back and win the mobile web again. If you're interested in learning about progressive web apps more, Mozilla, Google, and Flipkart, we are co-organizing a workshop on building a progressive web app from scratch. It's going to be on 25th and 26th of this week, and it's at the Mozilla office in Mountain View. If any one of you is interested to join that workshop, feel free to reach out to me or tweet to me, and I'll make sure you get an invite. With that, thank you. My name is Aditya Punjani.